Look at this simulation of rapidly mutating variables. Procedural programming breaks a task down into isolated data structures and subroutines. But when a system scales to thousands of entities interacting simultaneously, that separation of data and logic collapses under its own weight. Imagine a game simulation containing warriors, monsters, and inventories. If a monster steals a weapon, procedural code relies on discrete functions modifying globally accessible arrays. Every action mutates a shared state. The codebase rapidly degrades into an untrackable, tightly coupled mess where a single error corrupts everything. Object-oriented programming addresses these specific scaling failures by restructuring the relationship between data and the logic that manipulates it. Instead of leaving data and behavior separate, OOP bundles the descriptive state, like a warrior's health points, and the operations that change that state into a localized, cohesive unit called an object. OOP is an architectural defense mechanism. It strictly isolates state mutations within individual data structures, preventing a localized logic error from cascading into a system-wide failure. This diagram illustrates the baseline architecture of OOP. On the left is the class, a strict structural template defining attributes and methods. On the right is the Java code. When the program runs, it instantiates that class into an object, a concrete realization occupying physical space in heap memory. A single class can spawn millions of distinct objects. The program needs a mechanism to know exactly which instance it is modifying. The "this" keyword acts as a direct reference, pointing the JVM to the current executing instance in memory. If a data point applies to all instances uniformly, we use the static keyword. Notice the auto-incrementing entity ID above the individual objects. That static data belongs to the class itself and is shared universally, rather than being copied into the memory of every localized instance. To allocate that localized heap memory in the first place, the JVM calls a constructor method. This fires exactly once upon instantiation, setting up the required memory boundaries for the new object. Memory boundaries dictate system design. Modifiers like this and static give the Java virtual machine the explicit instructions it needs to distinguish between shared architectural rules and isolated instance data. Once the object exists in memory, the system must protect it. We establish this protection through encapsulation, the deliberate hiding of internal data, to shift access away from raw memory mutation toward controlled interactions. We enforce data hiding using strict access modifiers. In this diagram, the plus sign represents public access, the minus sign is private, and the hash represents protected access within a subclass. The mechanical advantage is straightforward. We declare the internal state fields as private, blocking all direct external access, while selectively exposing public methods to serve as the only bridge into the object. These public methods, specifically setters, provide structural validation. They act as gatekeepers, containing logic, like ensuring a deposited bank value is greater than 0, rejecting invalid state changes before they can corrupt the object. Encapsulation creates a rigid public contract. It guarantees that an object's internal state remains perfectly consistent, completely immune to unauthorized data manipulation from external system calls. As a system grows, separate entities often require identical baseline logic. A game's monster and player both need health points and a physics collider. Copying and pasting that shared code introduces severe structural vulnerabilities. The traditional solution is inheritance, which forms an I is a relationship. This diagram shows a monster subclass that is an entity, allowing it to automatically inherit all shared behavior located in the parent class. Contrast this with composition, which forms a has a relationship. Instead of drawing a vertical line to a massive parent class, the monsters simply hold a distinct weapon class as a private internal component. Modern software engineering heavily prioritizes composition over inheritance to maintain loose coupling.
Deep inheritance trees create fragile dependencies, where a single modification to the parent breaks every subclass beneath it. Selecting composition prevents system gridlock. Engineers can hot-swap individual component behaviors at runtime without dismantling the entire baseline architecture. To make those components universally swappable, the system relies on abstraction. The strictest mechanism for this is an interface, a perfectly abstract contract containing method signatures with zero implementation logic. An interface is absolute, whereas an abstract class offers partial implementation. An abstract class provides a foundation of shared code, while leaving specific methods blank for the subclasses to complete. Abstraction intentionally hides the how of an operation. It exposes only the what to the consuming system. A game engine knows an object can jump, but it remains blind to the specific physics calculations making the jump happen.
Programming to an interface enables the strategy pattern. The caller interacts only with the contract, meaning underlying algorithms, like swapping a credit card processor for a crypto wallet, remain interchangeable without altering the core checkout logic. Abstraction logically decouples the caller from the implementation. It allows engineers to write generalized algorithms that do not depend on the specific details of fragile concrete classes. We see the culmination of this decoupling in the execution loop. Consider an array of generalized entity references. In memory, those generic slots actually hold highly specific, distinct subclasses, like monsters and players. This code block displays the architecture. We defined an abstract entity base class, an independent movable interface, and the monster subclass that inherits the state of the entity and implements the contract of the interface. The polymorphic loop iterates over the generic array, uniformly executing the move method on every single object, ignoring their specific subtypes entirely. The JVM manages this via dynamic binding. It waits until the exact moment of execution at runtime to check the actual type of the object stored in heap memory, routing the generic call to the specific monster implementation. If the system needs to access a subclass-specific method, like triggering a dragon's fire breath from a generic reference, it enforces a safety check using the instance of operator before performing a downcast. Polymorphism reduces architectural complexity. It allows a central engine to trigger distinct behaviors across unique entities without requiring hard-coded conditional statements for every specific class. Failing to distinguish between overloading and overriding is a technical trap. Overloading occurs at compile time within the same class when methods share a name but differ in parameters. Overriding occurs at runtime when a subclass completely replaces an inherited method using an exact signature match. Attempting to override a method but accidentally altering the parameter types introduces a silent failure. The compiler processes it as a brand new overloaded method, entirely breaking the dynamic polymorphic loop. At the architectural level, the most dangerous trap is the fragile base class problem, caused by deep inheritance hierarchies. Textbooks frequently demonstrate 5-level deep inheritance trees, but applying those in production leads to catastrophic failure. Every child class becomes tightly coupled to the minor implementation details of its distant ancestors. Designing flat architectures built on composition over inheritance isolates your components. It guarantees that the system remains modular and extensible as business requirements shift. The procedural approach of loosely tracking global variables eventually buckles. By bundling state and behavior into localized objects, we provide the codebase with structural integrity. OOP requires 3 rules: encapsulate state, abstract behavior, polymorphic execution. Adhering to these mechanics marks the transition from writing code that merely compiles to engineering resilient architectures designed to scale. Thanks for watching. Subscribe to Insight Engine for more advanced technical breakdowns.